Okay, this will be the first in a series of lessons on air resistance. Up until this point, most of the problems that you've probably seen say air resistance is negligible, and you've derived and applied the kinematics equations to determine the position or the velocity of an object with a constant acceleration. Well, this time there's a force on the object causing a non-constant acceleration. And this problem that we're going to look at says, how far will an object travel if acted on by a force that is proportional to its velocity? So we're going to have an object traveling with some velocity here to the right and a resistive force in the opposite direction, and we're going to say that that resistive force is proportional to the velocity, which means that that resistive force, we'll call it F sub r, equals some constant times the velocity. Now, constant is going to depend on the certain factors like the shape or the surface area of the object and the density of the fluid that the object's traveling through, in this case the density of the air, and the force is going to be proportional to that constant times the velocity. So if you have this object that starts out at some initial velocity v, and it's going through the air and the air is slowing it down, how far will the object travel? So at the beginning, the resistive force is going to be pretty high, and as it travels, the resistive force is going to get slower, but that velocity is going to get slower as well until this thing comes to a stop. Now, typically when you're dealing with air resistance problems, you usually have two situations: one where the resistive force is proportional to the velocity, and another where the resistive force could be proportional to the square of the velocity. And which term you use or which term is dominant depends on several conditions that we'll talk about in a later lesson. This first lesson, we're going to focus on this one case right here and see if we can solve that. And before we clear the board and look at the math, because it'll come up later, let's just take a quick look at the units of B. And the units of the resistive force are going to be newtons, which breaks down to kilograms meters per second squared. And that's going to be the units of B times meters per second. Therefore, the units of this constant B are going to be kilograms per second. Just a good thing to put in a note somewhere. We'll come back later and do a little dimensional analysis to see if we did the math right. Again, that constant B is going to depend on factors like the size and shape of our object and the density of the fluid through which it's traveling. But we'll look at that later when we talk about things like when you use the linear velocity, when we use quadratic velocity or quadratic air resistance. So this video is going to be on horizontal linear air resistance. So let's take our diagram here again. Remind ourselves that we're dealing with the resistive force that is proportional to velocity, meaning that resistive force is equal to negative B times V. And the way we can start solving this, we'll start with Newton's laws. We'll say that the sum of the forces on the object, in this case, is just that resistive force. And we know that that equals, the sum of the forces equals the mass times the acceleration, and that equals negative B times V. We know that acceleration is the derivative of velocity, so we can say m dv dt equals negative B times V, and that gives us a differential equation that we can use to solve this. Box that in. So we'll solve this. If you look at this problem carefully, you might recognize that the best way to go about this is something called separation of variables. So I'm going to get all the terms with velocity on the left and all the terms with time on the right. And that leaves me on the left with dv over v equals negative b over m dt. And I'm going to integrate both sides. On the left, my limits are going to be time t equals 0, which I'll just write as 0, to time t. And on the right, I'll say at time 0, v is some initial velocity, v0, and we're going to go to time t at which the velocity will be v. Now, just to make matters a little simpler, to save myself some writing on the time, I'm going to make a little substitution here. I'm going to say let m over b equal tau. Therefore, negative b over m equals negative 1 over tau. And if you work out the units of tau, since it's m over b, that's kilograms over kilograms per second, which equals seconds. And that's a good note to have there for later. On the right here, when we integrate dt, we're just going to get t. And if we evaluate that from the limits from 0 to t, again, you just get t. So this is going to be, on the right, negative 1 over tau times t, or just negative t over tau. Saves us from writing t over m over b. On the left, well, I have dv over v, and that integral is going to be the natural log of v, and I'm going to evaluate that from the limits of v sub o to v. Now this should be the natural log of the absolute value of v, but our velocity has to be positive, so we can simplify this a little bit. Now again, on the left here, I can say the natural log of v minus the natural log of v sub 0 to take that, to evaluate that integral from our limits. And again, I can say that's equal to negative t over tau. Using what we know about logarithms, we can simplify this and say this is equal to natural log of v over v sub o equals negative t over tau. Now, we know that log base b of y equals x if b to the x equals y. Here our logarithm, the base is e, and that makes this v over v sub o our y term and this negative t over tau our x term. So we can say b to the x would be e, our base, raised to the power of this term over here. So v over v sub o equals e to the negative t over tau. And that gives us our velocity function. V of t equals the initial velocity times e to the negative t over tau. That's great. You may have a question that refers to that on your test, but the question that we started off with was how far does this thing go? So since we have a velocity function, let's go ahead and try to figure out our position function. Well, velocity was the derivative of acceleration, or acceleration was the derivative of velocity. Velocity is the derivative of position, so I can rewrite this velocity as dx over dt equals v sub o e to the negative t over tau. Again, we'll use separation of variables. I'll integrate from x equals 0 to x. I'll integrate from those limits the quantity dx, and I will integrate on the right side e to the negative t over tau dt. On the left, that gives me x, and on the right, this gives me negative tau v sub o e to the negative t over tau from the limits of 0 to t. Now, if I evaluate this integral to the limits from 0 to t, I get e to the negative t over tau, substituting in t for where I have t. And then if I substitute in 0 where I have t, I get e to the 0, which of course we know is 1. I'm going to distribute this negative right here across this term here, and I have a position function x of t equals v sub o tau 1 minus e to the negative t over tau. There's my position function. Okay, so I'm pretty close to the end. So first let's do a little quick dimensional analysis here. We said the units for tau are seconds. We know the units for time for seconds, so this value is a unitless number. So whatever this is inside the parentheses will be a constant, which means the units are going to be the units for x, which should be distance or meters, should be the units of the velocity times tau, which again is time. So velocity is meters per second, tau is seconds. Meters per second times seconds gives us meters. Looks like we did this pretty correctly. To find out how far this goes, let's take the limit of x as time approaches infinity. Well, this is 1 over e to the t over tau. Tau is a constant. As t goes to infinity, this value right here then becomes 0. So this value in parentheses just becomes 1. So the limit of x as t approaches infinity is v sub o tau. So how far will it go? You take your initial velocity and you multiply it by the time constant tau, which depends on your mass and your constant, your proportionality constant here, b, which again will depend on things like surface area and the density of the air, and you're going to come up with the distance. So one last thing to look at before we finish here. Let's take a look and see, you might get a question about the graphs of these objects. So if you have a constant velocity, we know that the position versus the time will be a straight line, and your slope is going to be delta x over delta t, and by definition that's your velocity. And if you graph velocity versus time, well, that's just a horizontal line. If you have a constant acceleration and you graph position versus time, of course you get the parabola, and your graph of velocity versus time will then be a straight line with your slope will be equal to the acceleration. For the condition that we just solved here, where the resistive force is proportional to the velocity, if you have position versus time, you're going to start off at x equals 0, at time equals 0, and you are going to have an exponential curve with an asymptote at v sub o tau. And velocity versus time, it starts off at some initial velocity, v sub o, and then your x-axis time is your asymptote. Now it's a good idea to see if you can start right here and go through this derivation a couple more times. The way that you might get asked a question can have several different forms, but they might ask you to justify your answer or prove your answer, and all the proof you need, the proof that you need to show will follow these steps in one form or another. So if you can do this derivation, you'll be pretty ready for any problem that you might see on a free response type question, or in, of course, test type question. Also, you're practicing a lot of what you learned in physics to this point. So here you have Newton's laws. Here you have differential equations. You're doing dimensional analysis. You're working with integral calculus. You're applying what you know about logarithms and exponential functions. Graphing functions and limits. So going through this derivation a couple of times is worth your while. And again, that's just the first quick lesson, just so you can see how you use the calculus that you learned in your calculus class and the physics that you learned in your physics class to solve a question about air resistance. And the next problem, we'll take a look at what happens when you have linear air resistance, but your object is falling. So you're dealing with two forces on the object, not just one. But that's the next lesson.